The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
The CDMA and the Cellular Standard, the IS-95, which is a kind of an old standard by now, but it's still widely used. There's still three major standards that are used for cellular communication, cellular voice communication. This is one of them. This is the one which is primarily being used as a jumping off point for all of the new standards that people are trying to think of. So I want to talk about it for that reason, but also because it really is a nice way of pulling together almost everything we've talked about in the course, because all of it comes into this one particular way of sending cellular voice. Okay, let's go through some of the details of it. Some things here might sound more detailed than what you're interested in, but I think it's good to have the numbers on it because it gives you some idea of which things, of which factors are really relevant and which ones aren't so relevant. So it uses a frequency band from 800 to 900 megahertz. Most of the new standards that people are thinking of are up in the gigahertz range, around 2 gigahertz or 5 or 6 gigahertz. I don't know the exact bandwidths. And all of these bandwidths depend critically on what the FCC wants to allocate, and also depend critically on which particular bands are good for electromagnetic propagation and which ones tend to absorb all of the radiation. Anyway, you use the band 800 to 850 for the reverse channel for the cell phones to the base, and you use the band 850 to 900 for the forward channel. Why do you want to separate the reverse channels and the forward channels by as much as you can? If you think for just a minute about the power levels at your sending antenna, either at the base station or at the cell phone itself, and then you think about how much power you're receiving, you see there's an enormous difference between these two, because things get attenuated enormously after they get transmitted. So what you're trying to do is to filter out what you're sending, which is an enormously high power, and you have to filter it out by enough so that it doesn't clobber what you're trying to receive, which means you need very good filters. And how do you build very good filters? Well, it's a lot easier to build good filters if you're not trying to make them cut off immediately. So if you have 50 megahertz, and you actually have a lot more than that. Well, no, you do have you have exactly 50 megahertz because this is all separated into a bunch of different channels. People in wireless, most practical communicators, when they talk about a channel, what they're talking about is a particular bandwidth. And all along, what we've been talking about is a particular medium going from transmitter to receiver. So what they're talking about is these channels. These channels or subbands are 1.25 megahertz wide each. We'll see what the significance of that is in a while. So you have a transmit and receive pair, which are both 1.25 megahertz wide and which are separated by 50 megahertz. So you have one channel down at the bottom of the range, another channel a little bit higher, another channel a little bit higher, and so forth all the way up. So you have lots of different channels, and you put lots of different cell phones in each channel for each base station. So that's roughly the overall architecture of it. It's the same kind of system that we've been talking about all along. You start out with voice waveforms, you have voice compression, you then have channel coding, you then have modulation, and then it goes out on the channel. And guess what happens when it comes back? You have demodulation, channel decoding, and then you turn it back into voice. So those are the three major steps, which we viewed before primarily as two steps. But all of the channel stuff is much harder than all of the source stuff. So let's talk about the source stuff first. The input voice gets segmented into these 20 millisecond segments. Why 20 milliseconds? Well, it sort of seems like it's probably a number that somebody picked out of a hat, but it's kind of striking that all of the standards use the same interval. And if you think about it a while, and I'll talk about this more on the next slide, but the reason for this interval is that in voice communication, delay is enormously important. You don't want to have much delay. And since you don't want to have much delay, you have to do encoding over very, very short segments. Well, anyway, what this does is it takes each 20 millisecond segment of voice and it maps it into 172 bits. And what that means is if you multiply the 172 by the 50 segments that you have per second, it comes out to be 8.6 kilobits per second. Now that might not sound like much of an achievement, but if you think about the old-fashioned way that people used to encode voice back in the time when they were first doing digital communication, what you would do was you would think of the voice as having a bandwidth that went from about 400 hertz up to about 3200 hertz. You would then view it as a baseband waveform from 0 to 4000 hertz. If you were going to try to sample that waveform, you'd have to sample it 8,000 times per second. And if you want good quality, you then have to use a large number of bits. You need a large number of bits for each sample. So the standard thing was to use 8 bits per sample. That gave you 64,000 bits per second in the old-fashioned way of doing it. People have worked for many, many years. Many engineers at the old Bell Labs spent their whole career trying to find out how to compress voice into smaller and smaller numbers of bits. And you know, 8.6 kilobits per second is still sort of a good rate. Is still a good rate if you insist that you have to do it in 20 millisecond segments. If you can take much longer segments to encode voice, you can do much better because voice really has a lot of constraints over relatively long periods of time. And if you try to, well, actually you know this, because if you take a person's voice and you map it into text, and then you also add a few things about pitch and things like that, you can really come by with a very small number of bits. But here you're constraining yourself to something that sounds like the actual voice and also has to be done in these 20 millisecond segments because of delay. So it still is a reasonably good achievement. All of the standards have figures about like this in the same order of magnitude. I expect that all of the new standards will do similar things. They will probably have slightly smaller numbers of bits. They will probably do much more computation, and they will achieve a little bit more because this is already, I think, relatively close to how far you can go. Okay, the next thing they do is they add 12 parity checks per segment. They use that for error detection. Don't want to talk about that a lot because it probably isn't necessary. All of the standards do something or other like this. The reason is if you take this 20 millisecond segment and you go through all of this enormous processing that we're going to go through, namely turning it into an encoded waveform, transmitting it, receiving it, detecting it, doing all the stuff we're going to do to it, if you get the 20 millisecond segment confused, and usually if you make errors, you make a lot of errors. So if at the receiver you wind up with the wrong thing, it is really going to sound awful. So they found that it's much better if you're not quite sure of what that segment is to just send silence for 20 milliseconds. And the silence is hardly detectable at all. It just sounds like good voice. I mean, for most of us, it really sounds wonderful to have a little more silence than well, enough of that. Okay, then there's another thing. There's an 80 8 zeros per segment that are added to this 172 bits as something which is called a terminator for the convolutional code. I might say a little bit about that, but not much. So what we've done is to add 12 bits and 8 bits to this 172 bits. That brings us up to 192 bits, which brings us up to 9,600 bits per second, which is what we're now going to try to transmit. Okay, so that's the voice compression part of the thing, and a little bits of overhead done for various special functions. The main reason I want to talk about these overhead factors is that every communication system I know starts out with very nice principles, studying very carefully what are the essential things, and by the time you get done with it, there are all sorts of little overhead items that get thrown in to make the thing work. And it's frustrating to everybody. It's usually 10% or 20% of the capacity of the thing, but it's always there. And that's why I bring up these two terms, because that's exactly the kind of things they're doing. They're just patching to make things work. So you have many details that lose all of the efficiency that you would like to have. Those are what makes it hard to compare different systems, because each system, architecturally nice though it might be to start with, always winds up with these little things because of these silly little constraints that say, since you have to have small delay, you have to segment voice into segments which are not much more than 20 milliseconds long, and those things cause you to do these other things. So that's where all of this comes in. Okay, all of the timing in this IS-95 cell phone system, everything is keyed to this 9,600 bits per second, and it's all keyed to this 20 millisecond interval. Everything is done in terms of 20 millisecond intervals. It's all a completely block system. The source generates 20 milliseconds worth of data. You encode that into 192 bits. That gets mapped into some code word, gets turned into some high-frequency waveform. At the output, you look at 20 milliseconds, and that gets turned back into your best hope of the 172 bits that you started with, and from there to some waveform. And every 20 milliseconds is completely independent of every other 20 milliseconds. You don't even save any knowledge about what the channel is between those periods of time. Everything is independent from one to the next. So the point is here, we've talked a great deal about all of digital communication sort of being generated from people's realization that they ought to separate voice coding from channel coding. In other words, there's this binary interface between all sources and all channels. This is a violation of that. And all cell phones have this violation. They don't have this pure separation because all of them face the fact that to do this small delay, anytime you want to get small delay, you have to have some mixing of what you do with the source and what you do with the channel, because the delay has to be some combination of what happens in both places. Okay, so we do have that violation, and it's because of interactive voice. You probably never thought about why it is that you need small delay on voice, but if you try to talk to somebody with a 50 millisecond delay in between what you're saying and what the other person is saying, you will find it turns you into a stutterer in about 5 minutes, everyone. Because the problem is we all have these social conventions that we use to tell us when we can start to talk when we hear silence from the other person. And if you have a break in that routine, even at 50 milliseconds, it totally screws it up, and both people start to talk at the same time, and it's very hard to have a conversation. So back in the early days of telephony, they found that about as much delay as they could tolerate was about 20 milliseconds, because when it got much longer than that, it gets very objectionable. If you talk to somebody on the phone who is in Japan, you have a little more delay than that, and you find it's very hard to talk to them. I mean, you have to practice a little bit. You have to think about it. If it's somebody for whom English is a second language, or you have Japanese as a second language, it's very, very easy, because then you both talk very, very slowly. So you catch up on that delay. But if you're both talking English very rapidly, or both Japanese very rapidly, it becomes hell on wheels. Okay. As far as the channel is concerned, we could also do very well by using longer code words on the channel. But again, we're stuck by this 20 milliseconds. Everything has to be blocked into 20 millisecond periods. Okay, so the first thing as far as coding is concerned is what's called a convolutional encoder. We unfortunately have not talked about coding at all in this course. We're not going to talk about it. I just want to say enough about convolutional codes so you get some idea of what they are. And here's the simplest example of a convolutional code that I think you can think of. You have a stream of input bits, which are coming in 1 per second. And each time an input bit comes in, that input bit sits at this dot here. I guess most people would prefer to put an extra memory element in, but it just complicates the diagram. So you have this input bit, you have the previous input bit, and you have the input bit before that. And what comes out at time j is a linear combination of this bit, that previous bit, and the one bit before that. And you call this a convolutional code with a constraint length of 2, because it has memory of these 2 bits. If you think about it a little bit, this is a device that has 4 states. Okay, because at time j, it needs to remember whether this bit was a 1 or a 0, and whether this bit was a 1 or a 0. So it's just a linear modulo 2 device that happens to have 4 states. And it produces 2 bits in each interval of time, which are functions of this bit and of the current state. In this convolutional encoder, which is used in IS-95, the constraint length is 8 instead of 2. In other words, you have 8 of these memory devices here. And the rate is 1/3 instead of 1/2. Here you have 2 bits coming out for each bit going in. There you have 3 bits coming out for each bit going in. But it's the same principle. If you think about it a little bit, as you increase the constraint length, the number of possible states that you have is going up very, very rapidly. Okay? So if you have a constraint length of 8, which means 8 binary digits stored there, you have 2 to the 8th different states, which is 256 states. If you added 1 more state to this thing, you would double the complexity of the well, it turns out that because of the way the decoder works, if you added 1 more bit to this block length, it would multiply the complexity of the decoder by a factor of 2. So when you try to decide how long these constraint lengths should be, you have to take into account that every time you make it 1 bit longer, yes, the thing is going to work better, but yes, also you make it twice as complex. And therefore, you have to wait another 6 months before you produce it at the same cost. So it's OK. We're going to use the Viterbi algorithm for decoding. If you don't know what the Viterbi algorithm is, fine. If you think in terms of finite state devices, think of it this way. You have a device here which has 4 states. Somehow, the decoder has to realize at each instant of time, if it's going to decode, it can either decode the bits here, or a nicer way to think of it is it decodes the state at each instant of time. If it decodes the state at each instant of time, it doesn't really have to have any memory. As soon as it knows what the state is at 1 unit of time, then it has a very simple decision to make to figure out what the incoming bit is and what the state is at the next instant of time. And what a Viterbi decoder is as something that does maximum likelihood decisions on the state. And there's a nice trellis diagram to talk about how that's done in the notes. You can read about it. It's interesting. Many of you have probably seen about it. It's sort of the easiest thing to explain as far as coding theory is concerned. It's the easiest thing to explain until you put all the notation in, and then whoever does it, as soon as they put all of the notation in, it becomes a bloody mess. But anyway, the idea is simple. Okay, so at that point we can sort of summarize what we've done as far as voice compression and channel coding. And so far, the IS-95 standard is pretty much the same as any other cellular standard. All of them, it turns out, use convolutional codes. Whether that's a good idea or not is another question, but they all do. It certainly is a very sensible thing to do. All of them use the same segmentation. All of them use similar techniques for doing voice compression. All of them have all these little overhead terms that come in. If you look at the numbers of what's going on, we started out with 172 bits per second, which was what comes out of the voice compressor. You then have these two overhead items. Incidentally, this 8-bit convolutional terminator, we can now get some idea of what that's for. You put in your 172 bits here. You're thinking of this thing in terms of the state at each unit of time. And if you're going to figure out what's going on at the end after you put in your 172 bits, you have to put in a couple of extra zeros to let this thing settle down. You have to let this bit go all the way through this device so you get enough data out about it that you can decode it. So that's what that terminator is for. It's for putting zeros in at the end of the sequence so you can view it all as one block code. So again, this is overhead which is caused by the need for small delay. If you didn't need small delay, that overhead term would be much, much smaller. Okay, so at that point, we're up to 9.6 kilobits per second, and we're up to 192 bits per segment. Then we go into this convolutional encoder, and the convolutional encoder multiplies things by a factor of 3. In fact, the rate 1/3 is a little bit different from most of the other standards, because one of the things that we're going to be doing here, since we're mapping this input into 1¼ megabits, that's a considerably broader band than these other standards use. The other standards are quite narrow band, and therefore they don't want to have a large number of bits per second. So here we're going to wind up with this talking about 28.8 kilobits per second at this point, which is 576 bits per segment, which is 3 times what we started out with. So we've expanded the number of bits by a factor of 3. If you question whether this makes sense to get a slightly smaller error probability through coding, but increasing your rate by a factor of 3, that's a perfectly sensible question to ask. And it just turns out that you do get a saving from that. And that's what all of coding theory is about, the savings, how much savings you actually get. But in fact, the savings are pretty considerable. So at this point, we're up here at 28.8 kilobits per second with 576 bits per segment. We then go through an interleaver. Don't ask yet what the interleaver is for. All the interleaver does is takes these 576 bits and it scrambles them all around. The receiver knows how they've been scrambled, so the receiver can unscramble them again. And why you need that is something we will talk about later, a good deal later. Okay, the next thing we're going to do, you thought you're through with coding, but no, in this system, there are actually 2 stages of coding that you go through. You can view one of them, though, as modulation instead of coding, and therefore you can claim you're only doing 1 stage of coding and 1 stage of fairly complex modulation. You remember when we talked about orthogonal code words, we said we could view orthogonal code words almost as easily either as a coding technique or as a modulation technique. Namely, you'd gather together lots of bits, and then you'd form code words which were signals which had a large number of dimensions in them. And we're going to do the same thing here. We are going to take this interleaver output, we're going to segment it into six-bit blocks, and then each 6-bit block is going to choose one of a set of 64 orthogonal code words. Okay? I mean, with 6 bits, you have 2 to the 6, which is 64 different combinations. So if you're going to use orthogonal code words, you need 64 of them. When we were talking about orthogonal code words before, we didn't quite know how to generate them. We then said last time that maybe using PN sequences is a nice way of doing it. That's not quite exact. Here, using Hadamard matrices is a nice exact way of doing it, and that happens to be the way it's done. And it's simple. I mean, you have a Hadamard matrix for each integer b. If you start out with b equals 1, which is 1 bit that you want to encode, you have a matrix which consists of two orthogonal code words, one of which is 0, 0, and the other is 0, 1. There aren't too many choices for that, and they're all equivalent. Then when you want to go to b equals 2, the thing you do is make a matrix, and the rows of the matrix are going to be the code words, and the columns correspond to the bits in the code words. So first code word here is 0, 0. Second code word is 0, 1. First code word here is 0, 0, 0, 0. Next one is 0, 1, 0, 1. And for orthogonal codes, the block length of the code and the number of code words is going to be the same. So the thing you do is you take this matrix, you put it there, you put it there, and you put it there, and then you complement the matrix and you put it there. Okay, why does that work? Well, if we just look at this part of it, this was an orthogonal code, this was an orthogonal code. In other words, each of these had half ones and half blah. Each of them differ from each of the others in half the positions, which is why you think of it as being orthogonal. This is a confusion that runs through all of communication theory, and we might as well get rid of that confusion right now. When you talk about binary sequences and you say they're orthogonal, what you mean is if you turn that sequence into a 2PAM signal, those corresponding signals are orthogonal. In other words, an orthogonal binary sequence, an orthogonal set of binary sequences, is a set of binary sequences where each of the sequences differ from each of the other sequences in half of the positions. And here with these Hadamard matrices, the way that's done is that one of the sequences is always all 0, and the other sequences are all half ones and half zeros. And it turns out that when you add any two sequences, add this sequence to this sequence, for example, you get something else which is half ones. And in fact, something else which is in there. That's what's called a group code, because when you add any two code words, you get another code word. Okay. Anyway, when you look at this, which is mapped into here and here, I mean, I think the argument is difficult here because it's too simple-minded, so you don't see it in its generality. Each time you go from one B to the next B, the thing you do is the same thing. You start out with this matrix, put it there, you put it there, you put it there, and you put the complement of it there. And what that does is when you look at the first half of the matrix, all of these differ in half the positions, because they differ in half the positions here, and they differ in half the positions here. So they differ in half the positions overall. When you look at everything down here, they differ in half the positions for the same reason, because complementing this doesn't change any of those distance properties. And when you look at the difference between these and these, it's the same kind of thing if you think about it for a couple of minutes. Okay, so this is an orthogonal code. Why do we want to use this orthogonal code rather than just an orthogonal code which uses the first degree of freedom and sends an enormous amount of energy, or the second degree of freedom sends an enormous amount of freedom, enormous amount of energy, and so forth? It's the same thing we were talking about last time with regard to channel measurement. You don't want to send enormous amounts of energy in any one degree of freedom. You want to spread it out over all of the degrees of freedom, and that's what all these codes are doing. All these codes are using 2 PAM on each degree of freedom to generate a code word, so the code words all have sort of uniform power in them. Okay, so at this point, we have gone into this orthogonal code generator with 28.8 kilobits per second. We have come out of it with 28.8 kilobits per second times 64 over 6. Namely, for each 6-bit segment in, we've gotten 64 bits out. So the total number of bits that we have has gone up by a factor of 64 divided by 6. So we're suddenly up to 307.2 kilobits per second. What we're trying to do is get ourselves, by hook or by crook, get ourselves up from these very small bit rates that we need to represent voice up to these large bit rates, 1.25 megabits per second, which we're going to spread this waveform to. All the reasons we want to spread the waveform, I'll talk about them later, but for now let's just think about it as saying somehow or other we want to spread the waveform out and turn a small number of bits into a large number of bits. So we've done a pretty significant part of that right here. If we think of turning these binary rows of the Hadamard matrix and modulate them by 2 PAM, we wind up with waveforms. The waveforms are orthogonal. If you wanted to think of taking these waveforms and then transmitting them up to passband, we would wind up with a bandwidth of 307,000 hertz. And that's not enough yet. We want to get up to 1.25 megahertz. Anyway, these waveforms are called wash functions. So the waveforms that you get from Hadamard matrices are called wash functions. You have to find something to honor everybody that's done a significant amount in this field, and Walsh was one of these people. So wash functions are quite famous, and all they are is just these orthogonal waveforms. So we now have an orthogonal code of length 64. The receiver, I'm going to talk about the receiver more later, but in essence, what it's going to do is take these 64 orthogonal waveforms. Only one of them will get transmitted in each of one of these, in each of these small units of time. So in the period of time corresponding to 6 bits into the encoder, we have to decode which of these 64 waveforms was sent. We're going to do that by using a Rake receiver, and that's what's used in IS-95. But this Rake receiver is different from the one we talked about. The one we talked about, we were making a decision between 2 hypotheses. Here we're making a decision between 64 possible hypotheses. So if you can remember the structure of that Rake receiver, it's sort of split into 2 separate sections. And one section was used for the decision on one of the waveforms, the other one on the other waveform. When we do this with 64 waveforms, it spreads into 64 different sections, which is why it's called a Rake receiver, because if you draw a picture of it, it looks like a rake. I mean, you start out here with a handle, and then you have it spread out into 64 different tines, and all of these tines have all of this signal processing going on in all of them. And then at the output, you come back and you change what your model of the channel is depending on the actual decision that you made. Okay, so So what we're using is a Rake Receiver, but a Rake Receiver which has 64 decision devices instead of 2. Suppose we go into an orthogonal code using 7 bits instead of 6 bits. Now, at this point, you're talking about real money, okay? Because at this point, you're talking about taking this Rake Receiver and turning it from 64 arms into 128 arms. Now, you can do that because these things are essentially free now, and computation is essentially free. But at the time when this was designed, there was a very hard constraint in terms of complexity about how many bits they can encode together into orthogonal waveforms. And I'll show you why in a little bit. It wouldn't have done them much better to have a larger set of orthogonal waveforms anyway. So anyway, it also uses incoherent soft decisions as a way of doing its detection. We talked about incoherent detection. This Rake Receiver uses that instead of the coherent detection that we talked about in class. And if you just put together in your mind the lecture we spent talking about Rake Receivers and the one we spent talking about incoherent detection, and you put them together, you have what this receiver is doing. And we'll talk about it just a little more as we go. Okay, if we now imagine these orthogonal code words, and suppose that each orthogonal code word has an energy, E sub s, and suppose for the time being that the channel is represented perfectly by a single tap model, and we know what the energy in that single tap model is. We don't know what the phase is, so we're using incoherent detection. What's the error probability? Well, the error probability for an incoherent receiver for making a decision between 2 possibilities was 1/2 times e to the minus energy divided by 2n0. Here we have 64 different possibilities, so we're going to transmit one of these waveforms, and we now use the union bound to say there's this probability of error to each of the other 63 possible waveforms. We could make an error to any one of them. It's equally likely to make an error to any one of them because they're each orthogonal to the one that we're dealing with. So this is a reasonably good bound on the error probability. Okay, now you go back from this to look at the reason why, one of the main reasons why you want to do this. E sub s is the amount of energy you use to transmit 6 bits instead of 1 bit. And therefore, when you look at the energy per bit that you're using, it's E sub s divided by 6. So your probability of error, if in fact you were making hard decisions at the output of this incoherent detector, would be in the order of 63 over 2 times e to the minus 3 EB over n0, which is a considerably larger exponent, and therefore a considerably lower error probability than we were getting when we were talking about transmitting single bits. In other words, the same thing is going on here as was going on when we were talking about getting up to channel capacity using a large number of orthogonal waveforms. It's the same idea. When you encode lots of bits together, you make a joint decision on all of them, you make a gain. Okay, and that's exactly what's happening here. You made a gain because you've taken the amount of energy that you have available for each one of your bits, and you've combined it all so that you get this bigger exponent in here. And if you're lucky, the exponent is big enough that it overwhelms this term, and your decision comes out with very small error probability. Well, as it turns out, we're not interested in making these hard decisions. What we're really interested in doing is just sending a likelihood ratio back to this Viterbi decoder, which it can use in making final decisions. But to see how well that's going to work, this is exactly the thing you want to look at, because this is what's telling you if EB is large enough, your decisions, if you had to make them, would be very good. And therefore, if instead of making decisions you pass likelihood ratios on, those likelihood ratios are going to have a lot of information in them. I mean, essentially, those likelihood ratios tell you what those code words are. Okay, now, the effect of fading is to change this E sub B, because when we were talking about this incoherent detection, we were looking at the energy per bit after going through the channel. Okay? So this is the error probability for a particular received energy per bit. So sometimes when the channel is badly faded, this number is very small. This bound is a lot bigger than 1, which you don't care about because the bound is no good then. And when the channel is good, this number is large, and this probability of error is very small, and your likelihood ratios give you a lot of information. If you have multi-tap diversity instead of a single tap here, if you have a lot of taps, you can visualize this as getting independent readings on the channel. And therefore, you can view it as getting independent information about the bits that were sent. And this is what diversity is. I mean, the trouble with these rarely fading channels is when they're faded, there's nothing you can do. But if you have multiple taps instead of one tap, then in fact you have diversity between all of them. If any of them are good, then you decode. Yes?
You were saying earlier that PAM is not ideal for the wireless channel. So why is the standard using PAM instead of why is the standard using 2 PAM instead of pulse position modulation?
Well, because it's using these long code words. Because back when we were analyzing it using 2 code words. And those 2 code words were orthogonal to each other. We could have made them +1, -1, and +1, -1 for the other one if we had in fact known what the channel was ahead of time. Okay? And that brings up a good point, because you have to get this started somehow. I mean, you have to know somehow what's going on at the channel at the point where you start. I'm not going to talk about that. Okay. If you have this multi-tap diversity, then E sub B is going to be better than it would be otherwise. This says if you can make the bandwidth bigger, as you make the bandwidth bigger, the bits are coming in faster, and as the bits are coming in faster, this bit time is the separation between the taps in this digital model, so that as you make the bandwidth bigger, you automatically get more diversity. You get more taps in this discrete model. Looking at it another way, you have a certain frequency coherence in the channel. If you're sending a broad bandwidth, you get lots of different frequencies, and if you get lots of different frequencies, there's a good chance that one of them is good. Okay, so we are going to get some gain in diversity there, and typically we're going to get a relatively large amount of energy if the thing works. Well, now we come to a question that we've been carefully avoiding all term. It's sort of the question of if you make code words orthogonal, or if you make code words have nice structure at the input to a channel, and the channel has some strange behavior, what's going to be the output of the channel? What we're doing here is making our code words orthogonal at the input of the channel. We can't guarantee that they're still orthogonal at the output. What we do know is that PN sequences are almost orthogonal anyway. And if you put PN sequences through anything, they still look like PN sequences. In other words, if you think of a PN sequence as an IID binary sequence, and you have a very long IID binary sequence, and you corrupt it in any way you want to, it still looks like an IID binary sequence. So the point is, if you can make these orthogonal code words look more like PN sequences, you can make them behave better at the output of the channel as well as the input to the channel. So you'll get something that looks orthogonal whether the channel essentially looks like a one-tap channel or a multiple-tap channel. Okay, we also have bandwidth to burn because we're only up to 307 kilohertz. So what they decided to do was to take a PN sequence and run it at 4 times the speed of this bit sequence. So we have bits coming in at 307,000 bits per second. We're going to have a PN sequence which is changing 4 times for each bit time. Okay? So suddenly we're increasing the speed of this whole system by a factor of 4. For every 1 bit, we multiply it by a sequence of 4 bits. So instead of getting a change every 1 over 307,000 seconds, you now get a change every 1 over 1.2288 millionths of a second. So suddenly you're up to a sequence which is right at the bandwidth you want. I mean, we wanted to get up to 1.25 megahertz, and suddenly we're up so close to that it's going to be a real challenge to build a filter which will really make the output look like it's limited to this 1.25 megahertz. So we need very tight filters here. If you multiply this PN sequence, you're using the same PN sequence on all of the orthogonal code words. And if you think just a little bit about it, if these orthogonal code words, I mean, think of them still as binary sequences. If each of them differ from each other when in half the places, when you multiply both of them by this PN sequence, they're still going to differ in half the places. Okay? So you still get the same effect out. They're still perfectly orthogonal before going through a channel, but now you have a good chance that they're pretty close to orthogonal after going through the channel. So suddenly we've gotten up to the bandwidth we want to be at. There's another reason for the PN sequence. I mean, so far we've been thinking in terms of how do you build a cell phone and a base station so they will work together. Actually, you want to build a base station and thousands of cell phones so they'll work together. So you want some way of making different cell phones look different from each other. And what they use this PN sequence for is to make different cell phones look different. So that each cell phone is going to start out on this PN sequence at a different point. The PN sequence is going to have a period of, well, it's going to be generated by a 42-bit feedback shift register. If you don't know what a feedback shift register is, don't worry about it. Most of you probably do. A 42-bit feedback shift register with the right kind of settings in it is going to generate a periodic sequence with a period of 2 to the 42nd minus 1, which is about 4 times 10 to the 12th. So it doesn't repeat very often. I mean, this really looks like an IID sequence of binary digits. And it really goes through every non-zero 42-bit combination in this period here. So it has very nice properties to it. But the property we want for this system is that, in fact, when you give a cell phone a particular setting in that shift register, it starts it off generating a PN sequence which looks totally different from that generated by any other cell phone. So that's the only thing that makes these different cell phones different, and it's enough to make each one of them look orthogonal to each of the others. Okay, their baseband sequences and thus passband waveforms are now going to be essentially orthogonal to those of other cell phones. In other words, at this point, we're sort of going into fantasy world. I mean, we started out generating 64 waveforms which were strictly orthogonal to each other. Then we said we want these waveforms to still be orthogonal after we go through this unknown channel. And we said, well, we can do this by making them look like PN sequences. But the other thing that PN sequences do is that all of the possible waveforms for one cell phone will look orthogonal to the waveforms for all of the other cell phones. So that in fact what's happening is if you look at a base station and the base station is trying to receive information from each cell phone, what it receives from one cell phone is going to be essentially independent of what it receives from the next cell phone. Now, if we think of the base station as trying to receive what's coming from one cell phone, what's the interference from the other cell phones going to look like? We're going to take thousands and thousands of sequences, which are now turned into waveforms, which look like IID waveforms, IID binary waveforms, and now we're adding together a large number of them. They fill up the whole spectrum uniformly, so they have a spectral density. I mean, it's a random process, and it has a spectral density which is flat over this bandwidth of 1.25 megahertz, and you've added a lot of them together, so it looks like white noise. So the effect of these other cell phones is just like a small addition of white noise as far as trying to detect what's going on at one cell phone. Now, in fact, you could be very, very clever here, because as soon as this base station decodes one cell phone, it can say, I know what that waveform was, subtracts it off from the received waveform, and uses that to help in decoding other waveforms. These standards do not do anything as sophisticated as that. Lots of papers talk about doing it. Information theorists love this idea. And it's, I don't know, I think it's one of these ideas that, that sooner or later it's going to become practical. And as soon as it becomes practical, everyone will use it. And what does it take to become practical? For someone to use it, because we all know it'll work, and it's just a matter of actually doing it. But anyway, it's not done now. But all of these interferers are just going to look like white noise as far as this one cell phone detection is concerned. Now, if we compare this IS-95 system with all of the narrowband systems that people use, at this point you can find the main difference between these different systems. When you use a narrowband system, things are arranged so that only one cell phone is talking to one base station on one of these narrow bands of frequency. Namely, the channels are very narrow, but because they're narrow, you don't get any, if you have two cell phones which are using that same bandwidth, they're just going to interfere with each other totally. You won't get through. So each cell phone which is using one base station has to be using a different narrowband bandwidth. The cell phones using different adjoining base stations are also going to have to use different bands. And in fact, that's a terribly complicated problem, because just because these base stations are put in sort of random locations and trying to program things in such a way that you don't have two cell phones which are using adjacent base stations using the same frequency is a real nightmare. So you're going to have cell phones using the same base station, which are a little bit separated, but still, because of all sorts of channeling effects and strange electromagnetic effects, base stations still receive data from these faraway cell phones, and they're also trying to receive data from the cell phone that's using that frequency. So you get a lot of interference in these narrowband systems from cell phones using different base stations. In the IS-95 system, you get more interference from cell phones that are using this particular base station because they're all using the same bandwidth. and they all just look like white noise to each other. So they do interfere with each other. They raise the noise level. But when you look at the interference with cell phones using other base stations, it's not catastrophic like it is with these narrowband systems. So what you effectively wind up with is that in the IS-95 system, you have more interference within a base station, but less interference between base stations. And in the narrowband systems, you have no interference within a base station, but considerable interference between base stations. Which is better? Nobody really knows. Well, except from the fact that almost all new systems are planning to use CDMA. It seems that most people have sort of agreed that you get less noise overall if you're using a CDMA system. Okay, so that lets us sort of summarize where we are with all of this. We started out with 28.8 kilobits per second. We've then gone into this wash function orthogonal waveform encoder, which comes out with 307.2 kilobits per second. We've then multiplied by this long PN sequence, 42 bits long, with 4 bits coming in here for each bit coming in here. Now we're implementing this, and anybody with any sense who was trying to implement PM sequences with multipliers would just say, I don't want to turn things into 2 PAM sequences yet. I want to keep them binary and add them mod 2 because that's easier. So all of this is still mod 2 binary digits. This is mod 2 binary digits. This is mod 2 binary digits. The only thing we haven't talked about yet is now they throw in 2 other PN sequences. One on the real part of what's going on here, and one on the quadrature part. The thing they're doing is taking this one sequence, splitting it into 2 parts, adding a PN sequence here, adding a PN sequence here, then doing the 2 PAM, then filtering and sending this stuff out on the cosine channel and this stuff out on the sine channel. I've never had a very good sense of why you need these 2 PN sequences here. I can sort of explain it to you in the following way. If you didn't have PN sequences here, what you'd be doing here is simply sending this same sequence twice. So you'd be sending on the cosine channel, you'd be sending it on the sine channel, which would sort of be equivalent to sending it at 45 degrees. And once you realize that, you say, well, I might as well leave this whole thing out and just use the cosine channel and nothing else. And if I'm just using the cosine channel and nothing else, it won't make much difference because the cosine just refers to the phase at this transmitter. And I'm talking about many, many cell phones whose transmitters are all at different places relative to a base station, and therefore they're all going to be using different phases, so they're all going to fill up this signal space. But the thing that doesn't take into account is the fact that if we do that, we're not using all the degrees of freedom available to us. We're still just using the number of degrees of freedom that we get here, which are real degrees of freedom. When we do this and this, we get twice as many degrees of freedom, so that the PN sequences that we're looking at, which are the things that are orthogonal to each other, we have twice as many bits in a given interval of time when we have these 2 PN sequences as we do when we only use this one PN sequence. So in fact, if we view PN sequences as IID binary digits, you get twice as many binary digits this way as you got before, and therefore everything works better. You come much closer to being orthogonal with higher probabilities. Okay, if you didn't understand that, fine. It's not explained in the notes either. It's not explained in the IS-95 standard, and I think the explanation is right, but it needs some fleshing out. Okay, here's another interesting feature about this Rake receiver. It doesn't use this digital model of the channel that we've talked about, and in fact uses the analog baseband model. Okay, in other words, it looks at the baseband model of the channel as the channel is represented by an analog filter. And the analog filter has impulses or almost impulses at different delays. And now what you'd like to do in this Rake receiver here is, instead of having taps at these sample times for the given bandwidth, you're going to adjust the taps so the taps are right on top of these things that look like impulses in all of these path returns. So the question is, what's the difference between these two strategies? I mean, we sort of showed that the digital model was completely equivalent to the analog model. But then I cheated you. I didn't realize I cheated you until about 9 o'clock this morning. But I cheated you in the following way. I told you that if you modeled the channel in terms of a discrete set of taps according to the sampling theorem, this was completely equivalent to trying to model it as far as a band-limited input was concerned in terms of an analog filter. And that's absolutely right if you use an infinite number of taps for the channel. If you now say that the impulse response of the channel is about 1 tap long, and then you say, how many taps do I need to represent it? That's an interesting question, because if the impulse response is 1 tap long, and you filtered it to look like a sine x over x, you can have the impulse response can look like this. So you have 1 tap here, 1 tap here, which is 0, 1 tap here, 1 tap here, which is 0. But if you've gotten your spacing off by half a cycle, what do you have then? You have a tap here, you have a tap here, you have a tap here, and you have these taps which are going down as 1 over time. So in fact, modeling this kind of thing with 1 tap would be terrible. Now when you use the analog filter and you actually put these taps of the Rake receiver at the places where you have actual physical responses, you do much, much better. And you particularly do better if the impulse response duration of the channel is of the same order of magnitude as 1 over the bandwidth of the source that you're using. Because at that point, this becomes an important issue. That's exactly the situation we have here, because the impulse response of these channels, 1 over the bandwidth of the input, the sample time on this discrete model is about 0.8 of a microsecond. If you think of how far light can travel in 0.8 of a microsecond, it's about the same as the multipath spreads you would find outdoors when you're in a relatively rural area. If you're in a city area, the multipath spreads are going to be even smaller. So if you want a Rake receiver to work well, you should really have a Rake receiver which is trying to zero in on the actual physical response times, which is what this system does. So they did it right and I did it wrong, okay? Okay, final thing. I told you I wanted to talk about why we did scrambling. This Rake decoder In other words, this decision device, which every 6 bits tries to make a decision on these 64 different orthogonal waveforms. You can just make hard decisions, which gives you 6 bits out each time, or you can produce 6 bits out also with some likelihood about how likely they are to be right. So what you'd like is some information which is essentially the logarithm of the probability of being correct over the probability of error. You can estimate that in your Rake receiver, and you can estimate it by knowing whether you're making a close call or whether there's one orthogonal waveform which is far more likely than all of the others. So if you're making a close call, then you produce an output that says, I think it's this output, but I'm not very sure. This is what goes into this Viterbi decoder. And the Viterbi decoder, since it's operating on these states, okay, in other words, it's operating on what it visualizes as being the state of the Viterbi decoder, it can actually deal with these log likelihood ratios as well as anything else. That's one of the reasons you want to use a Viterbi decoder, because most coding devices that people have invented don't work very well with analog signals. This does work well with analog signals. But the problem is, anytime you make a mistake on the 64 orthogonal waveforms, you have a 6-bit batch of digits, a 6-bit block, and you're going to be wrong typically in 3 of them. Okay, well, is that right? No, you're going to be wrong in a random number of them. Half the time you're going to be wrong in, well, what this means is if you put this data into a decoder, what you're going to find is that every time there's an error in the Rake receiver, you're going to have a burst of errors, some random bunch of errors over 6 bits, which is typically going to be in the order of 3 bits in error all at once. If you look at the structure of that decoder, anytime you got a large number of errors in all at once, it's going to screw the thing up terribly. Give you one example of that. If you take a much simpler coding example, suppose you transmit either all zeros, 7 zeros, or 7 ones. And at the receiver, there's a certain probability that you make an error on each one of these bits. Okay, you first make a decision on each bit, and then after that you make a decision on the whole code word. If the bit errors are independent of each other, then you make an error in the overall detection of these code words only when you make 4 errors out of 7. Or 5 errors out of 7, which is negligible. So you calculate what's the probability of making 4 errors out of 7 here. Well, it's a number of combinations of 7 things taken 3 at a time, which is 35 times p4, p to the 4th power, which is the probability of making 4 errors. If those bits are perfectly correlated, namely if whenever you make 1 bit error, you make all 7 bit errors, then the probability of error is p. And if p is relatively small, p is always a lot bigger than 35 times p to the 4th. Okay, in other words, the lesson here is that highly dependent errors cause trouble for any kind of decoder. Okay, now you see why you have the scrambler in here, why you have the interleaver. You have the interleaver to take these highly correlated errors which are coming out of the Rake receiver, where you make blocks of 6 errors, all tend to appear together. And you're scrambling them out so they're widely separated so that the Viterbi decoder is able to deal with them. So that's the last piece of the whole thing. I can talk a little bit about how the Viterbi decoder works, but I think you're probably exhausted by now, so I think I will stop at this point. So thank you all for your attention all term, and good luck in the final.